Hi, my name is Alekseishindin. I'm Associate Professor at Radiophysics Department of Lobachevsky University in Nizhny Novgorod, Russia. In this video, I present the report Study of Artificial Plasma Turbulence by Different Radiophysical Techniques at Arecibo Heating Facility in November 2018. First of all, I would like to thank the staff of Arecibo Observatory, Eliana Nosa, Mike Salzer, Phil Perlet, and Raul Garcia for a really warm welcome and support. Our team very sorry that Arecibo telescope is collapsed, and we hope that in future it will be reconstructed. We report preliminary results of the Arecibo heating campaign in November 2018. Different methods for studying artificial plasma turbulence were used concurrently, namely the incoherent scatter radar, ISR, and stimulated electromagnetic emission (SE) techniques. The aim of the experiments was analyzing HF-induced plasma turbulence evolution for short and long time of ionosphere modification above the low-latitude heating facility in view to investigate a competition between the Langmuir and upper hybrid plasma turbulence. The only experiments to date on simultaneous SE and ISR measurements has been carried out long time ago. Since that, the RF measurements technique have stepped far forward. In addition, a huge amount of results was accumulated in radar experiments, which for the most part received a fairly adequate interpretation. In this regard, the conduct of new joint experiments is of undoubted interest. The experiments were carried out on November 7-8. The ionosphere was heated by powerful radio wave of ordinary polarization with an effective radiated power 100 MW vertically at the pump wave frequency 5095 kHz for various radiated modes. The first mode is short pulses with low duty cycle with pulse duration from 5 to 100 milliseconds and pulse period from 2 to 20 seconds, so-called cold start mode, to study the formation of Langmuir turbulence. And the second mode is a quasi-continuous pumping with pulse duration 165 milliseconds and pulse period 200 milliseconds with a pulse train duration of from 1 to 150 seconds and simultaneous sounding by diagnostic pulses with pulse duration 0.2 to 10 milliseconds and pulse period 0.2 to 1 second for studying the processes of transition from Langmuir to upper hybrid plasma turbulence. The incoherent scattering radar pulses with a duration of 440 microseconds modulated by the lone random count with a repetition period 10 milliseconds at a carrier frequency 430 MHz. The delays of these pulses with respect to the pump wave start varied from 2.2 milliseconds to 7.8 milliseconds, which made it possible to study the evolution of the signal scattered by plasma turbulence at different stages of its development. As a result of the spectral analysis of the scattered radar signals, followed by averaging the data, the electron density profiles and artificial plasma line spectra, signals scattered by plasma waves with a spatial resolution of 300 meters, were obtained. For the short pump wave pulse radiation modes, from 5 to 100 milliseconds, scattered signal spectra were plotted relative to the central frequencies F plus minus, for the plasma line shifted down minus and up plus with respect to FR. In this case, the frequency shift delta F plus minus of the scattered signal frequency F from the central frequencies delta F plus minus corresponds to the shift of the plasma wave frequency FPL from F pump wave. In Figure 2, the results of such an analysis for the pulse emission regime with pulse duration 100 milliseconds and pulse period 20 seconds are shown. Together with the ionograms obtained by the unperturbed ionosphere sounding before start of the heating, the figure shows the artificial plasma lines shifted up and down near the frequencies FR 430 MHz, F plus 435.095 MHz, and F minus 424.905 MHz respectively. In the figure 3, the results of more detailed analysis of the plasma line spectra evolution for different heights and times from the pump pulse beginning for low-duty cycle program with pulse duration 100 milliseconds and pulse period 20 seconds are presented. At the stage of the Langmuir turbulence development, it was found that the maximum intensity in the spectrum of plasma waves is observed at zero shifts from F pump wave. Delta FPL is equal 0 at second 6 milliseconds of pumping, and the spectra themselves are of the continuum type in the negative shift range. Delta FPL is smaller than 0 at heights near the pump wave reflection level. With an increase in the heating duration to 12-20 milliseconds, the decay type spectra with pronounced maxima satellites at delta FPL between -12 kHz and -2.5 kHz are developed. A comparison of the integral intensity of the plasma line for pulse duration 10 and 50 milliseconds with one in 2.2 milliseconds after the pump wave pulse switching off made it possible to determine the plasma line relaxation time, which amounted to about half of a millisecond. This indicates that damping of plasma waves is collisionless with rate gamma is about 2000 Hz, since the collisional damping rate does not exceed nu E, which is about 500-1000 Hz. Note that the relaxation of different spectral components occurs with different rates, slowing down with an increase of the magnitude of delta FPL. As a result, at the relaxation stage, flattering and even inversion of the plasma wave spectrum can be observed. With an increase in the pump wave pulse duration, the altitude range occupied by the generation of Langmuir plasma waves increases from 1 km for pulse duration 5-10 milliseconds to 2.5 km for pulse duration 100 milliseconds. In general, the data for the stage of the Langmuir turbulence development are consistent with the previous results at the Arecibo facility. According to the references 5 and 6, with an increase in the pumping duration to seconds or minutes, the plasma turbulence region expands downward from the pump wave reflection level up to the heights of the upper hybrid resonance and lower. In our experiments, for long, about 2.5 minutes pumping, an expansion of the altitude region of plasma wave generation up to 7.5 kilometers, up to 15 kilometers for pumping near the critical frequency of the F2 layer, and its stratification are observed. The time altitude dynamics of downshifted plasma line development during the first 15 seconds of quasi-continuous pumping is shown in the figure 4. Two regions of plasma line excitation were observed with the intensity maxima at the heights 214 km and 210.8 km. In the upper region, near the pump wave reflection level, the decay type spectra with intensity maxima were observed at the first and second seconds of pumping. Intensity of such spectra weakened to the 14th, 15th seconds of pumping. In the lower region, at the heights near and below the upper hybrid resonance, the plasma line was amplified to 14th, 15th seconds. Here the spectra look as broadband maxima in the range for delta FPL between -40 plus 10 kHz, with a peak intensity at about -10 kHz. An analysis of the concurrent measurements of the SE and signals of incoherent scattering can substantially clarify details of ionospheric plasma turbulence excitation. Such experiments were performed at Arecibo, HARP, and ISCAT heating facilities. The first such comparison was performed in the reference 7 for pump wave frequency 3125 kHz at the initial stage pumping and had shown a similarity of the plasma line and SE spectra up to 50 milliseconds. Examples of the SE spectra at the initial short pulse stage of pumping and during long heating for experiments are shown in Figure 5. Our measurements of the plasma line and SE also show a similarity of the main spectral characteristics of the plasma line and SE, the continuum shape of spectra with the widths up to 30-40 kHz at the stage of Langmuir turbulence development during first 100 milliseconds. During longer quasi-continuous heating, the formation of the main upper hybrid SE feature, such as downshifted maximum at frequency shift is about -8-11 kHz, correlates with the observed characteristics of the development of the broadband maximum of the plasma line in the lower part of the plasma turbulence region. However, the spectral shape of the SE and scattered signals differ noticeably. Since the data of radar sensing provide information on only one of the components of the spatial spectrum of plasma waves, wavelengths 35 cm for Arecibo radar, it is difficult to expect full compliance with the SE measurements, since SE generation and ground-based reception are determined by the integral influence of the entire spatial spectrum of plasma waves. During concurrent measurements of the pump-induced plasma line and SE, it was established the following. With increasing pump time from milliseconds to hundreds of milliseconds, a transition from the continuum plasma line spectra to decay-type spectra is observed while the SE is kept in continuum shape and the SE intensity decreases. From the first second to 10th seconds, the plasma line decay spectra generated near the pump wave reflection point weakened and even dropped till 15th second. In the same time, the broadband plasma line maximum at lower by about 3 km altitudes and well-structured SE spectra with well-pronounced upper hybrid components develop. This points most probably for shielding the region of Langmuir turbulence generation near the pump wave reflection point by upper hybrid turbulence. The relaxation process of plasma waves and SE is accompanied by flattering of their spectra and, as a rule, is collisionless with rates gamma bigger than mu e. That's all. Thank you for attention. In this slide you can see the full list of used references.